environment, we will look at distributed file systems, MapReduce and Hadoop, and some MapReduce algorithms. So in terms of distributed file system, we will look at breaking data into chunks, replicating the data, and distributing it on racks. The standard architecture for that is a cluster of commodity nodes, which are called compute nodes. That is just a computer which has a processor, a memory, and a disk. The way we connect these nodes is through network connection. So Ethernet connection is for local area network through wire, so they are wired. And gigabit is the speed of the network. So 1 gigabit per second is sent between any pairs of two nodes in a rack. So this is a computer. It has a CPU, memory, and a disk. It is connected through Ethernet network or switch, so through local network connection with a wire to the other computer. You can transfer 1 gigabit per second. A rack like this, a rack of nodes like this, can contain 16 to 64 nodes. So between 16 to 64 computers it will be on this rack. So imagine a bunch of racks like that. So this was one of them with 16 to 64 computers. That's another one. And there's going to be more here. All of those are connected through a faster network, which is from 2 to 10 gigabits per second backbone. So that's called a backbone because it's a pretty fast network that is used to connect these racks together. So that's how the clustered architecture looks like. Now, some of these nodes can fail when they're doing the data processing. So what are we going to do to resolve this issue? So we do need to replicate the data and store it in several places in order to avoid that issue. And the way we do that is by creating a special file system, which is called a distributed file system. And this distributed file system provides a global file namespace. So the file has a global name, which can be accessed from other nodes. Some examples of this is the Google Global File System, Colossus, and the Hadoop Distributed File System. If we have a file or a data set, we can split it into multiple pieces. So it is split in contiguous pieces or chunks. Contiguous means that they are in order, in the original order. Each piece could be 64 megabytes. Then this piece or chunk is replicated. It means that we keep multiple copies of that piece in several different places in case one of them fails. So usually 3 times the piece is replicated. And then we try to keep these replicated pieces on different racks in case one of them will fail. The master node for the file will store the information about the file. such as the name of the file, the size of the file, who is the owner, when it was last modified, and things like this. And also contain a record for which is the first and the last piece of this file, and where are all the pieces located. What if this breaks? What if this master node will fail? Can we recover the file?
There is a secondary master node.
Okay, so we can try to, yes, we can try to keep multiple copies of that, for just in case, because these machines that we just have seen here, they are these machines, these are not some special high quality servers. These are cheap machines. They don't have very fast CPU or too much memory. So any of those can fail really at any time. So this is a cluster of small cheap commodity computers. So this is what happens. These are the racks. We set between 16 to 64 nodes in each rack. And then that's the file. The file has 1, 2, 3, 4, 5 pieces. So we're gonna, each one is about 64 megabytes. So we're gonna split it into those pieces, and then each of the piece is replicated 3 times and placed on a different node. So the orange piece, the yellow piece, as you can see, is here. The red piece is in 3 different places. The blue piece is also. So hopefully, if any of those pieces will fail, then we can use obtain the chunk from another node. Now there's another way to do that. There's a way to code those pieces, so if some of them is lost or broken, we are able to restore it. So there is less redundancy if the possibility of loss happens, but then if we only have one copy, then we don't have a choice of where we're going to obtain that copy. So let's say, if we have 3 copies, some of those one of them could be closer to us than the others. In this way, we incur less cost, less network traffic, and faster processing to get to it. If it's only one copy, we don't have a choice of where we're going to get it from. Let's look at what is MapReduce. So we will do a brief introduction and a word count example, and then we will think about how this little program will perform if one of the nodes fail. So what does the MapReduce give? Easy parallel programming, invisible management of hardware and software failures, and then able to leverage very large scale data. So this was designed to allow us to break the data into pieces and process each of those in its separate nodes. The nodes themselves are managed by that distributed file system that we have seen earlier. So it's either Google's global file system or Hadoop distributed file system. So if any of the pieces fail, that background system will take care of it by giving us the piece which is stored in another node. The MapReduce, so we don't have to care as a programmer of MapReduce of how that works because that's handled for us. And it allows us to easily design programs that will process in a parallel environment. So the MapReduce job starts with a collection of input elements of a single type. Usually these are key value pairs. So we do have a key value pair. We will apply a function, a map function, to the key value pair. And each input element, which is that key value pair, is done in parallel. How is that happening? Because there is a mapper that applies the map function to a single element, and they could be many of those mappers, and if we group them together to process the job, then that will be called a map task.